Hello, my name is John Moyer, and I want to welcome you to the NIH Office of Disease Prevention's Mind the Gap webinar series. This series explores research design, measurement, intervention, data analysis, and other methods of interest to prevention science. Our goal is to engage the prevention research community in thought-provoking discussions to promote the use of the best available methods and to support the development of better methods. Before we begin, I have some housekeeping items. You can submit questions during the webinar via the chat pod. You'll need to open the pod by hovering your cursor at the bottom of the Zoom window and then clicking on the chat icon. Please direct your questions to hosts and panelists. We will open the floor to questions that have been submitted via the Zoom chat pod at the conclusion of today's talk. The slides and video recording will be posted on our website, prevention.nih.gov/mindthegap, in approximately 2 weeks. Lastly, we would appreciate your feedback about today's webinar. Upon closing, you will be asked to complete an evaluation. We would appreciate your feedback as it will help us improve this webinar series. Unfortunately, Dr. Murray can't make it to today's webinar, so I shall introduce today's speaker, Dr. Jennifer Thompson. Dr. Thompson is an assistant professor in the International Statistics and Epidemiology Group at the London School of Hygiene and Tropical Medicine. She is co-leader of the methodology theme within her group, as well as the quantifying impact theme in the Center for Evaluation. Her expertise is in developing and evaluating analysis methods for step-wedged and parallel cluster randomized trials and identifying more efficient trial designs. She has also been the statistician on several infectious disease treatment trials in low and middle income countries. It is my pleasure to welcome Dr. Thompson.
Thank you for that introduction, and thank you everyone for joining us today and for inviting me to give this talk. Today can I first check that you can hear me and see my slides?
Yes, thanks.
Excellent. So today I'm going to talk to you about why I think you should consider using randomization tests to analyze your step wedge trials. The analysis of most trials is by design usually very simple, but what can make it more difficult is that we need to pre-specify what we're going to do. Most analysis methods require some assumptions to be made, and we have to anticipate what assumptions are going to be appropriate for our trial data before we see that data. We can end up in a bit of a difficult situation if our chosen analysis methods turn out to be inappropriate for the data we have, potentially even giving misleading results. We can make things easier by choosing analysis methods that either don't make as many assumptions or are robust against the assumptions that they do make. A really simple example of this is a t-test. It assumes that data are normally distributed, but it's been shown to give valid results, even if data are as skewed as the figure shown on the left here, or are as have the kurtosis shown on the right here. A step wedge trial is an example of a trial where pre-specification of the analysis can be difficult. A step wedge trial is a type of cluster randomized trial, sometimes called a group randomized trial. And for these, we randomize groups of individuals rather than the individuals themselves. So this could be things like hospital wards or schools or geographical areas. In a step wedge trial, we randomize these clusters to switch from the control condition in the light green on this slide to the intervention condition in the darker green on this slide, and they'll switch at one of several time points spread throughout the duration of the trial. So at the start of the trial, all or most of the clusters are in the control condition, but by the end of the trial, all or most of the clusters are in the intervention condition. An example of this that we'll come back to throughout this talk is a step wedge trial of a tuberculosis diagnostic test, which was conducted in 2012. The trial was testing the impact of switching from the standard test for initial TB diagnosis to a new, more sensitive diagnostic test. And one of the outcomes they looked at was the impact this would have on patients' response to their TB treatment. This is a schematic of the trial design. The clusters were laboratories, and at the start of the trial, all laboratories enrolled in the trial were using the standard test, and they began enrolling patients diagnosed at these laboratories for 1 month, while all of those laboratories were still using the standard diagnostic test. Then 2 of the laboratories were randomly selected to switch to using the new diagnostic test, and patients would continue to be enrolled, with every month 2 more laboratories switching to the new diagnostic test. So by the end of the trial, all of the laboratories were using the new test. Now, the problem with pre-specifying the analysis of a step wedge trial is to do with the correlations in the data in these studies. In all cluster randomized trials, we have to account for correlations in the data, which are similarities between observations in the same clusters. So the total variability in the data around the overall mean can be split into the variability of cluster means around the overall mean, and then the variability of individual observations around their cluster means. And in a parallel cluster randomized trial, that's all you need to take into account. We have several analysis methods to account for this, which we can easily pre-specify. In a step wedge trial, these cluster means won't stay the same throughout the trial because we're collecting observations over time. We might have a time trend in the data. It could be that this time trend is the same for all clusters, or it could be that these time trends are slightly different for different clusters. And this can lead to changes in the correlations over time. If the changes over time vary between clusters, then after we've adjusted for the overall time trend, the correlation within clusters will reduce over time. So observations collected closer together in time will be more similar to one another than observations collected further apart in time. The same can happen with the intervention. If the intervention varies between, the effect of the intervention varies between clusters, then an observation collected under the control condition will be more correlated to another control observation than it would be to an intervention observation from the same cluster. We don't know which of these factors are going to vary between clusters when we're writing our analysis plan. So we need to be wary of analysis methods that require us to specify this in advance. Randomization tests, which are also known as permutation tests, can help overcome this problem. They appropriately account for the correlation between observations without having to specify a structure for those correlations. So what is a randomization test? Let's start with a really simple individually randomized trial. We have some data collected under the control condition in the yellow dots here, and some data collected under the intervention condition in the blue dots here. And we use these to estimate an intervention effect, theta hat. If the intervention hadn't had any effect, it wouldn't have mattered who had received the control or the intervention conditions. We would have expected to see a similar result. And we can mimic this in our data by mixing up the labels of control and intervention for each data point. So some of the yellow points are turned blue and some of the blue points are turned yellow. And then we re-estimate our intervention effect with this new mixed up assignment, and we get theta 1 hat. We can do this many times for lots of different reassignments of control and intervention labels. And eventually, after say 1,000 different allocations, we end up with a distribution of intervention effect estimates under a null hypothesis that the intervention has no effect. Now, a p-value is defined as the probability of observing the same or a more extreme result than the one we observed under the null hypothesis that the intervention had no effect. So this is our null hypothesis of no effect. And our p-value is simply the proportion of these mixed up assignments that resulted in a p-value the same or more extreme than the one we observed. For a step wedge trial, we do a similar thing, but we want to honour the structure of the data and honour the randomization scheme. So rather than simply mixing up the individual control and intervention labels, we'll mix up when clusters switch from the control to the intervention. So say we have this step wedge trial shown on the left here, and this gives us our intervention effect theta hat. We can mix up the assignment of when the clusters switch and get a new intervention effect theta 1 hat. And for another assignment and another, and so on, until we end up with that distribution under the null hypothesis of no effect. Now you'll notice in talking through this, I haven't specified the correlation within structures at all. Instead, we just need to honour the structure of the data and the randomization scheme when we reassign the control and intervention conditions. Now, I've been quite vague so far about how to estimate the intervention effect. And that's because there's a lot of flexibility in what you can choose as your estimand and how you estimate it. There's several things you might want to consider with this. One is efficiency, and another is how robust that method is against the assumptions it's making. One potential option is to use a mixed effects model. Mixed effects models specifically model that correlation structure of the data to estimate the intervention effect and adjust for time trends. The benefit of this method is it's very efficient, but the drawback is that it assumes that correlation structure is correctly specified. And if it's incorrect, then the effect estimate could be biased. And this makes them quite difficult to pre-specify in an analysis plan. We demonstrated both of these points in a simulation study we published in 2017. The simulation study was motivated by this influential step wedge trial conducted in Kenya in 1998, looking at the impact of deworming school children on their school attendance. In this trial, the time trends did vary between clusters, but there was another complication in the data as well, that the variability in the data reduced over time. So on the left here, we have data from the control arm of the trial, and on the right here, we have data from the intervention arm. The y-axis of these figures shows the log odds of school attendance for each school enrolled in the trial. And you can see that for both control and intervention, there's much more variability in these log odds of school attendance in the first year of the trial than there is in the second year of the trial. And we were interested in what the impact of this complex variability looked like in the effect of on the analysis methods. So we conducted a simulation study based on this data, and we generated 500 data sets to mimic this trial data. And that's the bottom scenario shown on the figure here. We also simulated some simpler data structures. At the top, we have a data structure with observations equally correlated within clusters. And in the middle, we have a scenario where time trends did vary between clusters. So correlation reduced over time, but we've removed that extra complexity of decreasing variability over time. So for each of these scenarios that we simulated, we have 500 data sets, and we analyzed each of those with 3 different mixed effects models that each make different assumptions about the correlation structures in the data. The dots on this figure show the mean estimated intervention effect for each scenario, and the bars around those dots show the interquartile range of the intervention effect estimates. In the simple correlation scenario shown at the top, all 3 analysis models are correctly specified, and they all estimate the intervention effect without bias and very accurately. In the other 2 scenarios, the green analysis model is correctly specified, and the orange and purple models are incorrectly specified. So the green correctly specified model does estimate the intervention effect without bias, but both of the other models estimated the intervention effect with bias, and the effects are much more variable than the correctly specified analysis method. So based on these simulations, we would not recommend using a mixed effects model to estimate the intervention effect for a step wedge trials. The correlation structure tends to be very uncertain when you're writing your analysis plan. And if you pre-specify an analysis method that turns out to be inappropriate for your data, you could end up with a biased estimate of your intervention effect. An alternative is to use a within-period analysis method. It's much more robust, but it is less efficient. There are several different approaches, but today I'm going to focus on using a cluster-level analysis calculated within each period. So here we have a step wedge trial, and a step wedge trial can actually be split into several mini parallel cluster randomized trials between the cluster switching, like this. So within each of these mini parallel cluster randomized trials, we can use any analysis method that's valid for a parallel cluster randomized trial to estimate an intervention effect and get a variance for that intervention effect. The first step is to summarize the outcome in each cluster. So say you had a binary outcome, this could be the proportion of patients with your outcome in each cluster in each period. Next, we use a t-test to compare the control observations and the intervention observations within each period to get an estimate of the intervention effect and a variance for that intervention effect within each period. We can then combine these using the inverse of the variance as weights. So the estimates with a higher variance are given lower weights, and an estimate with a lower variance are given higher weight to get an overall intervention effect estimate. Okay, so now we have a method to estimate the intervention effect, and we can use randomization tests to calculate a p-value. So let's work through our tuberculosis diagnostic test example. So recall that the trial had 14 laboratories that were switching from a standard diagnostic test to a new diagnostic test, and we want to look at the impact on patients' treatment outcomes. So now we're going to calculate an odds ratio for reducing unfavorable treatment outcomes. So first, we're going to calculate a log odds of the outcome in each cluster in each study month. We then compare those within each study month to get a log odds ratio for each month. On the odds ratio scales, this range from 0.62 in month 4 all the way up to 1.03 in month 2. Our comparison in each month can also give us a variance for this log odds ratio, which we then invert and convert into a weight. So these weights vary from 0.05 in month 2, so 0.03 in month 7, all the way up to 0.43 in month 5. So when we combine these log odds ratios using these weights, we get an overall odds ratio of 0.78. We can then conduct a randomization test using this method, and this gives us a distribution of intervention effects under the assumption that the diagnostic test has no effect on patient outcomes. We did 1,000 different randomizations, and only 18 of those gave an intervention effect the same or more extreme than 0.78. So this gives us a p-value of 0.02. So I've explained what a randomization test is and one way to estimate an intervention effect to use with one, but does this method work, and is it more robust than a mixed effects model? So to look at this question, we published a simulation study in 2018. The simulation study was based on publicly available data from the NHS on the uptake of free health checks. We generated 1,000 data sets for different step wedge trial designs, looking at an intervention aimed at increasing uptake of these health checks. In this publicly available data, the time trends did vary between clusters, which were different areas of the UK. So the correlation within the data did reduce over time. And we looked at several different trial designs. So for each data set we generated, we analysed them with a mixed effects model that assumed time trends were the same for all clusters, and with using the within period analysis with randomization tests that we've just worked through. So this slide shows a selection of the results of that simulation study. This scenario at the top here is data that fully represented the publicly available data from the NHS. At the bottom here, we have another scenario where correlation did reduce over time, but we've reduced the amount of correlation in the data. Within each of these correlation scenarios, we have 4 different trial designs. The top one has 11 clusters randomized to switch at each of 11 time switch points. So that gives us 121 clusters. We also have 11 clusters switching at 3 switch points, so 33 clusters, and 3 clusters switching at each of 11 switch points, again 33 clusters. And lastly, 3 clusters switching at 3 switch points, so 9 clusters overall. This figure shows the confidence interval coverage of each of the 2 analysis methods we analysed the data with. The mixed effects model, which is incorrectly specified for these scenarios, had very low confidence interval coverage in all of these scenarios that we're showing here. The randomization test, on the other hand, has very good confidence interval coverage across all scenarios. These results show another benefit of randomization tests, and that's that they work well even with a small number of clusters. This last trial design has only 9 clusters in it. And you can see the mixed effects model has particularly low coverage in these scenarios, because mixed effects models require a small sample adjustment to be used with very small numbers of clusters. The randomization test, on the other hand, maintained very good confidence interval coverage, even with 9 clusters. The main limiter on the number of clusters to use with randomization tests is the number of ways there are to randomize the clusters between the different switch points. With 9 clusters randomized between 3 switch points, there's actually well over 1,000 ways to randomize those clusters. If, on the other hand, you had only 6 clusters to randomize between 3 switch points, there's actually only 90 ways to randomize the clusters. So then the smallest p-value that you could get with a randomization test is 1/90, which is equal to 0.01. And this reduces the power of the randomization test. There's been several other papers that have looked at the performance of permutation and randomization tests with step wedge trials, and they've all found quite similar results to ours. So I've shown that the randomization test is a more robust method of analysis, but this does come at some costs. So I'll talk through some of those. The first drawback to using randomization tests is efficiency. Well, actually, randomization tests are as efficient as a parametric method of analysis. The efficiency really depends on the method you've used to estimate the intervention effect, and within period methods are less efficient than some other methods. Methods like mixed effects models also utilize comparisons of the control and the intervention within clusters, because in step wedge trial, you generally have control and intervention observations within each cluster. The within period methods don't utilize this information, and that makes them less efficient. This is something we looked at in the NHS simulation study. So this slide shows the relative efficiency of the mixed effects model for estimating the intervention effect compared to the within period cluster level analysis. We have a different subset of the results from that simulation study to what I showed you previously. At the top of this table, we have some results where the time trends vary between clusters. And at the bottom, we have some results where we simulated data with the same time trend in all clusters. For each of these, we have either 3 switch points or 11 switch points, but we've only shown results where there are 33 clusters in total. And then we have a low ICC or a high ICC for each of those scenarios. So that's a low correlation between clusters or a higher correlation between clusters. This column on the right shows the relative efficiency of the mixed effects model and the within period analysis. If this number is less than 1, that means the within period analysis is more efficient. And if the number is greater than 1, that means the mixed effects model is more efficient. When the time trends varied between clusters and the number of switch points is low, there's actually very similar efficiency between the two analysis methods. We have the same efficiency with the low ICC and better efficiency for the within period analysis method with a high ICC. However, when we have the same time trend in all clusters, or we have a large number of switch points, we tend to have more efficiency with the mixed effects model estimator. This scenario at the bottom has the same time trend in all clusters, 11 switch points, and a high correlation between clusters. And the mixed effects model estimator is 6 times more efficient than the within period analysis. So it depends a lot on the data you've got and how strong the correlations are, whether you think the time trends vary between clusters, as to what to estimate the relative efficiency will be between these methods when you're choosing between them. Another drawback that's often mentioned with randomization tests is that they're actually testing a slightly different test to the parametric tests we're more used to. A randomization test tests a null hypothesis that the intervention effect has no impact at all on the outcome, whereas parametric methods only test the average effect of the intervention. A randomization test p-value will be small if the intervention has an effect on the average, like the parametric method would, but also if the intervention has no effect on average, a positive effect in some clusters, but a negative effect in others. So there's a variable effect of the intervention. The result is valid, it's just answering a slightly different question to what we're used to with parametric methods. You're unlikely to know in advance whether your intervention effect is going to vary between clusters. So I like to plan to do some simple analyses and produce figures like this one shown on the slide. This figure has the time in the study on the x-axis. Here we have the study month. And the outcome on the y-axis. This figure is showing data from our tuberculosis diagnostic trial example. So on the y-axis, we have the prevalence of favourable outcomes. We have a light blue line for the standard diagnostic test, the control arm, and we have a dotted dark line for the intervention, the new diagnostic test. And we can see the mean of the outcome for each month. And the bars around this are one standard deviation either side of that mean. So some measure of variability around that mean. If you can see a visible difference between the lines, like you can for this one, but the variability between the control and the intervention is similar, this is indicating that your randomization test p-value is small because of that average difference in effect. But if you had lines that were overlapping a lot and the intervention line had much more variability around it than the control line, that would indicate that your randomization test p-value is small because of that difference in variability, because the intervention is having a variable effect rather than changing the average outcome. For our TB diagnostic test, though, we can see here the variability is similar between the lines, and there is a visible difference between control and intervention. So it's likely that our small p-value is because the intervention really does have an average of improvement in favorable outcomes. Where I've been talking through the steps of how you would do this analysis method, it may have sounded a little bit complicated, but we've written a stata command that does this whole analysis method in one line of code. So you can use any analysis method you like to calculate your intervention effect, run it with our stata command, swpermute, and it will conduct a randomization test to provide you with a p-value. It can also do the within period analysis method that we've discussed here today. So thank you very much for listening. I'd like to finish by acknowledging my collaborators in the work I've presented today. That's Callum David, Catherine Fielding, James Hargreaves, and Richard Hayes. And I'd like to take this opportunity to give a little plug to a short course I'm a co-organizer of at the London School of Hygiene and Tropical Medicine. The course is on the design and analysis of cluster randomized and step wedge trials. And there is a link at the bottom of the slide here if you are interested in joining us. It's running the week of the 26th of June, and it's hybrid, so you can come to London to join us face-to-face or join remotely online. Thank you very much, and I look forward to your questions.
Thank you so much, Dr. Thompson. It's an excellent presentation. We have some questions coming in. We have, with these randomization tests, we can calculate p-values, and they depend on the selection of random allocations. I guess there could be a concern about implications for the reproducibility of results, like possibly cherry-picking results. You have any comment on that?
Yeah, so the simplest thing to do is set a randomization seed before you run the randomization test. I think I had a slide that showed some results for this. Yeah. So if you set a seed, which you can do with our command, or you can just set the seed before you run the command, then you'll get a reproducible result that will always give you the same random selection of allocations, and you'll get the same number that are more extreme than your observed result. The other thing you can, and if you pre-specify what seed you're going to use, that would be important too, to add to your analysis plan. And another thing you can do is use a large number of allocations. So because there's this random element, stata command gives you a confidence interval around your p-value. So you can see whether your the number of repetitions you've used gives the interpretation of that p-value would vary if you'd picked a different selection of allocations. So in this example here, we have a very, very small p-value, and you wouldn't change your interpretation of the result based on this confidence interval around this p-value. But if this confidence interval went up to, say, 0.1 or something, where you might have a slightly different interpretation of your results, you might want to increase the number of randomizations you used until this interval gives you a more consistent interpretation of the results.
Great, thank you. So on one of the slides, it was a cluster level analysis within period slide where you were calculating the treatment effect estimator. It kind of showed like one of the mini cluster randomized trials, one of the sequence. I think it was 32 maybe, yeah, this over here. One more forward.
This one?
Sorry. One more maybe forward, I think. A couple more.
Forward this way?
Yeah, sorry. Yeah, right here. This okay.
This one.
This one. Thank you. Yeah, sorry about that. I wasn't. Yeah. So, question. So, kind kind of the middle three periods are used to calculate the treatment effect estimator. Is in the kind of the leftmost and rightmost period, like the leftmost, there's no intervention being conducted. In the rightmost, it's all intervention. Do those periods factor into the in any way to the calculation of the estimator?
So they can do, and they can do, and what they haven't in what I've shown here, but you could adjust for this period, for the baseline period and the post-intervention period in your calculations here. So I've said use a t-test, but you could use a regression analysis and include data from this period and the first period and the last period in that regression. But also you could, if you were planning to do a within period analysis, you could design your trial so that you didn't have periods at the start and the end with all clusters in the same condition.
Okay. And if you have kind of a situation where there's like maybe only one cluster in the intervention and the rest are not, does that pose any complications to calculating the?
I think if there's only one, you probably won't be able to. I'm not sure if there's only one. You definitely won't estimate it with very much accuracy in that period.
Right,
I don't think you could, because you've got no reproducibility within that condition.
Right, that makes sense. So you showed, so certainly we can calculate, you showed how to demonstrate how to calculate p-values. Can you create confidence intervals with the permutation test approach?
You can. That's another limitation that people often say with this analysis method. I had a couple of slides on that. It's a little bit more involved than with a parametric method. So you're always testing that your control observations and your intervention observations, there's no difference between them. But your confidence interval is an interval of effects where there would be a p-value of greater than 0.05. So you can test different null intervention effects to find which intervention effects would fall within your confidence interval. And the way you would do that would be you would subtract the null effect, a null effect test from the intervention observations, and then run the randomization test on this new edited data, see if that fell within your confidence interval, and then do another test of that to see if another effect fell within the confidence interval until you worked out what that confidence interval would be. So here I've got a table of a really, really simple example. We have 8 observations and they go from 1 to 8. The first 4 were in a control condition and the last 4 were in an intervention condition. So say we wanted to test a difference of 4, we keep our control observations the same, but we subtract 4 from each of the intervention observations. And then we run our randomization test on this new edited data. And that would give us a p-value for whether there was evidence of a difference between control and intervention with this new data. And that would tell us if this difference of 4 would fall in our confidence interval. In the Stata command paper that I showed you, we give a kind of step-by-step how you would do this without having to test millions of values to work out what that interval would be. So first of all, you could estimate what the confidence interval would be if it followed a normal distribution. So your p-value is based on, say, your intervention effect and a standard error around that and a normal distribution. So you can invert that to work out a standard error for what a normally distributed confidence interval would look like around your intervention effect. And then you can use that estimated standard error to calculate rough interval values. And that would give you starting points for values to test for the boundaries of the confidence interval. So with our TB diagnostic trial example, our intervention effect was the log of 0.78 and our p-value was 0.018. When we invert that p-value, we get a standard error of 0.1, and that gives us a rough confidence interval going from minus 0.45 to minus 0.04. And we can then work through testing values around those rough limits to find out what the permutation test interval would look like. So if we test minus 0.45, which was our estimate of the lower bound, that has a p-value of 0.09, which means it would be inside our confidence interval. But then we test a value of minus 0.5, that has a p-value of 0.04, which means it falls outside the interval. Minus 0.48, that's just inside. Minus 0.49, that's just outside. So that gives us a boundary of minus 0.48. So our lower bound for our odds ratio would be 0.62. And we can do the same for the upper bound and get a confidence interval upper bound of 0.95. So it can be done. It's a little bit fiddly, but you don't actually have to test that many values to get those limits. There have been some quite interesting papers of showing algorithms for how this can be done automatically, which is something I'd quite like to implement in that state of command in the future.
Great, thanks. So, the randomization tests and mixed effects model approaches can, perhaps give slightly different results. I guess, what are your thoughts on in stating in the analysis plan that both approaches will be conducted and, based on any correlation structures observed or any influence of time trends?
I think I'd want one to be specified as the primary, because otherwise you could get cherry picking if it says both are going to be done. If one shows an effect and the other doesn't, you risk that being the one that shows an effect being used as the primary, even though it wasn't specified it was going to be primary in the analysis plan. Yeah,
definitely don't want to avoid the cherry picking of results, definitely. So do randomization tests like the ones you've described have bias due to using a weighted average of a non-linear metric, like the odds ratio in your case, as a non-linear logistic regression would? And I guess if that's the case, does that give an advantage to the model method because that bias can be decreased by the inclusion of important covariates?
Do you mean bias in the estimated effects?
Yes, I believe so, yes.
It wouldn't, because you can use any method to estimate the effect. So it's the randomization test component is just for the p-value. It's just for the uncertainty around those effect estimates. So you could use a logistic method if you wanted to use an odds ratio scale. And then you've got whatever biases your method you've used to estimate the effect has or not.
Okay, thank you. So one big threat to internal validity in a step wedge trial is when clusters cross over. Like, it's very important that they stay on schedule. In the randomization approach, are clusters, is it still important for them to cross over on schedule and not allow any kind of any cluster transitioning too early or too late? Does that have any impact on the randomization test?
Yeah, I think there's a bit of a question, I guess, with not just for randomization tests, but step wedge trials generally, when there is if they switch at a slightly different time, in the data, do you label the observations as intervention at the time they were meant to switch or at the time they actually switched? So it's not really a randomization test question. It's generally a step wedge question, and it is important because with a step wedge trial, you're inducing confounding between your intervention effect and time because of your intervention observations are later in time than your control observations. We know that there is that confounding, so we can adjust for it. But if this switch point moves because of something related to the outcome, so say you're in a hospital and you're at a particularly busy time of year, so patient outcomes are slightly worse than they would normally be, and so that means you delay introduction of the intervention, then that can cause a bias in your intervention effect estimate, because you've just given lots of poorer outcomes to the control condition. So you really want to make sure you're not inducing any bias by relating the time you introduce the intervention to what the patient outcomes or your trial outcomes are. And that's whatever analysis method you're using.
Okay, thank you. So you mentioned in one of your previous slides, there was like a mixed effects model seemed to do well when there was really no time varying trends between clusters. I guess how common do you think it is for time trends to vary in that way between clusters?
It's a little bit of an unknown at the moment. So when we were planning our simulation studies and looking for data, we weren't hunting around for data sets where the time trends varied between clusters. They were just the ones we found first, essentially. But on the other hand, the TB diagnostic trial that I've been presenting here, I don't think the time trends did vary between clusters in that data set. So it isn't all data, but I think it probably is quite common. I think there's maybe more research needed to look at when it's like settings where it's always, the time trends are pretty much always going to vary between clusters, and settings where it's very uncommon and you can be a little bit more confident in using a mixed effects model.
Okay. So somewhat on a similar tack, there's some thoughts on time varying intervention effect, perhaps based on some exposure time. For example, the standard step wedge trial usually assumes like it's like a light switch. You as soon as you transition to the intervention condition, it's an immediate and persistent intervention effect. Are there any adjustments that might be made if using randomization tests to analyze such data?
So I think the main adjustment would be you really want to think carefully about what your estimand is. What is it do you want to estimate? So I've just brought up a schematic of a step wedge trial. So John's talking about where you have say a smaller effect when the intervention is first introduced, and then it gradually increases over time. Or it could be you have if it's training intervention, maybe you have a large intervention effect when it's first introduced, and then it reduces over time. And in a step wedge trial, you've got your different amounts of information about different intervention effects then. So you have quite a lot of information about the immediate effect of the intervention, because all of your clusters have a small amount of information about the immediate effect. But you don't have very much information about the longer term effects of the intervention, because fewer clusters are in the intervention for a longer time. So when you have this variable intervention effect, you need to think about what it is you want your primary intervention effect estimate to be. Do you want it to be some average of these different intervention effects over time? And then think about how you're going to estimate that. There's some great papers out there looking at different estimators, different estimands, different summaries of all these, because you have lots of different intervention effects now. You can summarize those in different ways, and then different ways to estimate that. And then the good thing about the randomization test is it gives you a way to estimate a p-value for any of these estimators that you want to use. But it's a really good point, John. It's a hot topic at the moment, and people use step wedge trials without really thinking about how their intervention effect might vary over time. And then you need to put a lot of thought into what it is you really want to estimate. And the randomization test can be really useful for the p-value and confidence interval for whatever you decide you want to estimate there.
Excellent, thank you. Let's see. Could one use a mixed model rather than a cluster level analysis within person? So in this analysis, you wouldn't lose within cluster information, and then layer a randomization on top of that, a test on top of that. And or does the bias potential in the mixed model remain even if you were to layer a randomization on top of that?
Does this mean are they talking about the within period?
Yeah, within period, yeah.
Yeah, so you could use a mixed model within period, yes. So then I've actually got a paper on the comparison of cluster level analysis and mixed models for parallel cluster randomized trials. So they both perform quite well. With mixed models, they don't perform so well with a small number of clusters, and with step wedge trials, you tend to have a small number of clusters. So your within period analysis, you would have quite a small number of clusters because you've still got the same number of clusters, right? The intervention, I think you're not very likely to have any bias in the intervention effect estimates because you're only looking within period and making comparisons between clusters. So I don't think bias would be an issue. The variance might not be estimated very well with a mixed effects model within period because of the small clusters issue. And a benefit could be that if you have variable cluster size, you might get a bit more efficiency using a mixed model rather than the cluster level analysis.
Okay. If bias isn't a problem or isn't thought to be a problem, why not use the mixed model with bootstrap for variance estimation? Is there any disadvantage to that approach?
I think you could do. I'm not sure how you would implement the bootstraps because bootstraps, depending how they're implemented, can have issues with the small number of clusters. But there's lots of different ways to implement bootstraps. So I'm sure there is a method that can be used with a small number of clusters. And that would be an option. Excuse me, the bias with the mixed effects model is mainly if you've got a binary outcome. If you have a linear outcome and using a linear mixed effects models, you don't really need to worry about the bias in the same way.
Okay. And I guess kind of on a similar approach, is there some definition of small number of clusters, or is it kind of dependent on each case?
I think for a mixed effects model, it's around the 30 mark off the top of my head. I'm trying to think what we found in our paper. I think it was around about 30, maybe slightly higher, 40 clusters.
Yeah, that sounds, I think, yeah, it's kind of the classic,
yeah,
infinity occurs at 40 sort of
yeah.
assumption that's made, right?
Yeah, generalized estimating equations, you need even more. You need 50, 60 clusters for them to not need any small sample corrections.
Right. I guess on that topic, GEE is designed to be robust to these misspecified correlation structures. Are they a good alternative to randomization tests?
They are, yes. You need to use small sample corrections. So the estimated standard errors tend to be too small if you have a small number of clusters, as we were just saying, maybe less than 50-ish. So you need to use small sample corrections. I have a paper on generalized estimating equations for step wedge trials as well. And we find some small sample corrections that work quite well with them. We had some issues with convergence with exchangeable working correlation structure with the generalized estimating equations. So there are some issues with that method, but it is a good alternative.
Okay. So you had your SW permute as for Stata. Are you aware of any similar commands in R or SAS?
Not really. I've found one for clustered data for SAS in SAS, but I don't think it would work for step wedge designs because it's clustered and you have control and intervention within each cluster. I would like to, I hope in the near future to write a command for R. I may get onto SAS if I get lots of emails after this webinar asking for a SAS command.
Great. I guess as the, I guess as a quick question. So someone had a question for your GEE paper. Are you listed as first author? Is there?
Yes, I am.
Great. I guess as the probably the last question. With these re-randomization tests, or with these randomization tests, you randomize, you know, essentially kind of change the sequence to which the clusters are assigned. I know one kind of approach to randomizing or to allocating clusters, constrained randomization. So we create a list of pre-specified allocation schemes, and that's usually helpful, especially when there's a small number of clusters. Is there any challenge or I guess, yeah, any challenge to using this technique, allocation technique, with randomization tests and step wedge trials?
It can actually be a really good matching of design and analysis. So you can limit the allocations that you pick from in your randomization test to the ones that you allowed in your randomization of clusters. So you can have a big data set that has all of the randomizations you were choosing from, and only use those in your randomization test. And it can work really well to maintain type 1 error and maximize the power and really utilize that design that you've used. And then I think you don't need to adjust for the factors that you've used in the constrained randomization.
Great. Well, thank you so much, Dr. Thompson, and thank you to everyone who participated in today's webinar. On the Mind the Gap website, prevention.nih.gov/mindthegap, you will find several resources for this talk, including the list of references and slides. We will also be posting a recording of today's webinar on our website in a few weeks. Thank you and have a great rest of your day.